So today we're going to look at electron orbital diagrams. So what this is an extension of our electron configurations. So what we're basically doing here is we're going to take an electron configuration, which we've learned how to make using the periodic table, figuring out where the atom is, and then going through the steps, 1s, 2s, 2p, so on and so forth. We're going to take that and we're going to put it now in a diagram. And this diagram relates to the structure of an atom. So in order to fill an electron orbital diagram, we need to follow a set of rules. So we need to know the rule definitions and then how to apply them once we start filling in our little map here. So we have Hund's rule, the Aufbau principle, and the Pauli exclusion principle. So I'm going to start with the second rule. The Aufbau principle basically just tells us to start filling at the lowest energy level first. So start at lowest energy level. So basically all that really means is you want to start at the 1s and then go to the 2s and then the 2p. So you start at the lowest and work your way up. Okay, so you notice I have an energy sign over here and the energy increases as you go up. Let's relate this to the structure of an atom. So how I have the electron orbital diagram drawn is you can imagine the nucleus as being here. Okay, much like this nucleus, this red nucleus in the center. So we have the nucleus with the protons and neutrons present in it, and then we have these energy levels or these rings surrounding the nucleus. And those energy levels are where the electrons reside. Now, this first energy level, n equals 1, that's the same as the 1s energy level. Okay, this energy level is closest to the nucleus. Since it's closest to the nucleus, those electrons are held very tightly. Because remember, the nucleus is a positively charged center because of those protons in the nucleus. So it's got a positive charge. So since it has a positive charge and electrons have a negative charge, opposites attract. So the closer those negatively charged electrons are to that positive center, the tighter they are held. Okay, so if they're held very tightly, they're more stable, they're lower in energy. But the further those electrons get away from the nucleus, the less tightly they're held. And since they're held less tightly, they have a greater energy, and so they're going to be easier to pluck off. That's why the valence electrons in the outermost shell, those are the electrons involved in bonding. So they're involved in bonding because they're held less tightly. They're easier to take, and they're more accessible, right? They're on the outer ring. So this means that we want to start when we fill in electrons at the lowest energy level. Okay, so we'll start at energy level 1, and then we'll go to 2, and then to 3, so on and so forth. So that's what the Aufbau principle is saying. So Hund's rule only really applies to p and d orbitals. So it's not going to apply to the s. So what Hund's rule says is that electrons should singularly occupy an orbital before pairing up. Okay, so let's look at an example to explain this. So with a p orbital, remember the p sublevel has 3 orbitals. So that's why when I wrote the 2p and the 3p sublevels, I have 3 lines. Because these 3 lines are representing my 3 orbitals. So this is representing a p sublevel with 3 orbitals in it. So when I'm adding electrons to this p sublevel, Hund's rule tells me that I want to put 1 electron in each, and when we draw electrons in this, we're drawing them as arrows. Okay, so I want to put 1 electron in each before I pair it up. Because electrons are negatively charged, so they want to spread out as much as possible. Because negative charges are going to repel each other, right? The same charge repels. So they want to be as far apart as possible. They don't want to pair up unless they have to. So this would be a correct example of 4 electrons in the p sublevel. Now, if I were to draw 4 electrons in a p sublevel like this, that would be incorrect. Because what I did was I paired them up and I have no electrons in that empty orbital. Okay? This is wrong because they don't want to pair up unless they have to. So I want to spread them out and I want to put 1 in each and only pair them up when I need to. Okay, so that's what Hund's rule is saying. Spread them out. All right. Now, the Pauli exclusion principle is going to be the last one that we look at. And what the Pauli exclusion principle is saying is that no 2 electrons should have the same quantum numbers. Now, I know that might sound confusing. Basically what it's saying is that when we look at one of these empty spaces, we look at one of these orbitals and we put electrons in, we want to make sure that they have opposite spins. So what that means is when you draw the electrons, since we're representing them as arrows, you want to draw one arrow going up and the other arrow that's present in the same orbital needs to be going down. Okay, they need to have opposite spins. If you were to draw, so this is an empty orbital here, the electrons with both arrows up, that would be incorrect. They need to have opposite spins, one going up, one going down. So that's what that rule is saying, okay? So let's write out an electron configuration. We're going to pick a neutral atom, write down the electron configuration, and then we're going to fill in this orbital diagram using these rules. Okay, so I'm going to pick, let's do phosphorus, okay, because that's going to make use of all of these rules for us. So phosphorus, I'm talking about the neutral element phosphorus. And if you're following along with your periodic table, phosphorus is number 15. It's in period 3. Okay, so we're going to write our electron configuration using the Aufbau principle. We're going to start at the lowest energy level, which is energy level 1. We hit the S block first. 1s2 brings us to helium. Then we go to the next energy level, row 2. We hit the S block first. 2s2 brings us to beryllium. Then we're still in period 2. We hit the P block next. We want to go all the way through the P block to neon, which brings us to 2p6. Then we're in period 3. We hit the S block first. We go to magnesium, which is 3s2. We want to keep going in period 3. We hit the P block, and phosphorus is in the 3 Ps. It is actually 1, 2, 3. It's the third one in. All right, so now I'm going to use a different color. Let me use blue here. I'm going to take these electrons and fill them in. And remember, these superscripts, these are representing the electrons. Okay, so they should add up to 15 since we're talking about a neutral atom. So since phosphorus is number 15, that means that phosphorus has 15 protons. Since it's neutral, the protons are going to equal the electrons. All right, so I'm filling this in with 15. When I fill it in, I'm going to start at my lowest energy level. So I'm going to start at the 1s. When I put my electrons in it, I only want 2 electrons in each of these empty spaces, in each of these orbitals. And when I put the electrons in those empty orbitals, I want to follow the Pauli exclusion principle and make sure they have opposite spins. Once I get into the 2p and 3p, I'm going to use Hund's rule and make sure that I only pair up electrons if I have to. All right, let's start. We're going to go down here. So the 1s, so it can fit 2 electrons in it. So I'm going to put 1 electron up and 1 down. So I've used 2 so far. For the 2s, same thing, 1 electron up, 1 electron down. I'm at 4. I get to the 2p and I'm going to put 1 electron in each before I pair them up. So notice there's a total of 6 electrons in the p because that's the max that we can fit in the p orbitals. So we're here, 2p6. 1, 2, 3, 4, 5, 6. Okay, now we go to the 3s. We're going to put 2 electrons in the 3s. one up and one down, following the Pauli exclusion principle. And then notice for the 3p, 3p3, so we're only going to have 3 electrons in the 3p. When I do this, I do not want to do this. That is incorrect, because this is not following Hund's rule, which says spread out the electrons. Don't pair them up unless you have to. Okay, so that was incorrect of me to do. What I want to do instead is I want to put 1 electron in each orbital. And since 3 is the only amount I need, I don't have to pair any up. So this would be the correct electron configuration, or electron orbital diagram, excuse me, of phosphorus. You can even check and see that it matches up with that as well. So on your homework or on an exam, if you had to pick an electron configuration, orbital diagram, excuse me, or fill in an orbital diagram, they wouldn't represent it like this vertically. So instead, it would be written horizontally. So they would have 1s, 2s, 2p, 3s, 3p. But you're still following the same rules and it would still look the same. Okay, so you would still want to have arrows going opposite directions for each empty space. And you don't want to pair up the electrons unless you have to. Okay, so these are representing the same thing. There's just different ways to represent them. That's electron orbital diagrams.